Hi, I'm Boris Cergol. Welcome to my talk. So, first let me say a few words about the relationship between software engineering and machine learning. So what we have seen, especially in recent years, is that there were a lot of best practices coming from software engineering to machine learning. So let's say CI/CD, versioning, data management, microservices, containers, and so on. So this is really great as it is making machine learning more efficient and applicable in the real world. Also, one strong trend is using machine learning to make machine learning itself more efficient. For example, through efforts like AutoML, neural architecture search, and so on. So one question, of course, now is, in what ways will machine learning make an impact in software engineering? In my opinion, one of the biggest impacts will eventually happen because of automatic program generation. So in automatic program generation, we start with the program specification, and then basically an AI system generates a human-readable program that is satisfying the specification. So in cases when it actually is a human-readable program, we call it program synthesis. But when the result is not interpretable in human language, we call it program induction. And this is mostly because in these types of models, the program is implemented in some latent part of the AI system. So there are quite different ways of setting up program specifications. I have written here some options here since they tell us a bit about potential applications of automatic program generation. So one way that is especially common in research literature is to make a specification using input-output pairs. So in this case, program synthesis becomes programming by example. But we could also give incomplete code with the command to complete, or faulty code with the command to repair, and we would get code completion, program repair, code migration if we would be moving from one programming language to another. And then there is let's say out of this, at least the most general part is multimodal program synthesis. And here the specification is given in different modalities, in code, natural language, there could be screenshots, and so on. So actually, program synthesis is one of the oldest problems in AI. So it goes back to at least to the 60s. But actually, for the first 50 years of work on this problem, most of the results were quite theoretic. So why is that? So why is program synthesis such a hard problem? Let me get into this a bit. So the first reason is program space intractability. So the space of all the potential programs is really large, especially for general purpose languages. So in order to make this problem a bit more feasible, often we introduce domain-specific languages, which are kind of restricted. Often they are also more faster to run, and so on. However, although this solves some of the problems, it introduces different ones, and one of them is lack of data. Since when we move to domain-specific languages, we often don't have a lot of code that is generated by humans in kind of real-world settings. So we have to solve lack of data, and often this is done by generating synthetic data. But this again can be problematic if not done well. Can really cause a lot of problems, and these problems often manifest themselves in generalization. So often programs don't generalize well to distributions that are not the same as the training distribution. Then there's another line of issues regarding specifications. So specification multimodality can be quite challenging because we have to deal with natural language and potentially image recognition and so on. And all this is also causing difficulties in user intent interpretation, especially in the real world settings. This is quite a difficult problem. And of course, also usually there is an infinitely many solutions that comply with the given specification. However, that does not mean that actually all of them, even though correct, would indeed be best or useful for the user. So there's a whole question of what potential evaluation metrics to use to find programs that are better. And then there's a list of other issues, so more related to the structure of programming languages and programs themselves. So they are really based on kind of discrete structures, and often, especially certain kinds of models have issues or have difficulties in making good representations of these discrete structures. So the vocabularies can get quite large, since developers have a free hand in naming variables and other objects. There are long dependencies. So, for example, variable is defined somewhere in the beginning, and then there's a long program, and only then it is used, and also rich structure. So there are different levels of abstractions in programming languages and code. And also everything is very sensitive to changes. So a small change in the input might mean a totally different outcome. And all of this is difficult for machine learning approaches. So nevertheless, also deep learning made quite a big impact on the field of program synthesis. So in neural program synthesis, many models are at least vaguely in the form that I have listed here. So encoder-decoder structure in kind of sequence-to-sequence type models, where there are, for example, input-output pairs that are put through the encoder to get embeddings, and these embeddings then go to the decoder, which is usually some sort of recursive neural network to get programs. And as I've said, there's good success with these approaches, but also there were many deficiencies. So it seems like this type of structure doesn't take full benefit of the structure of the code of programming languages. There are questions also about issues with generalization beyond the training distributions, how to make good discrete representations. So quite a lot of issues, and this is why in program synthesis actually two machine learning paradigms meet, so neural and symbolic. So both have a long history. A lot of that history is in many ways antagonistic. However, especially in the area of program synthesis, there seems to be that each one of them has certain strengths, and it would be sensible to combine them. So there is a very influential paper that was written by Gary Marcus, The Next Decade in AI, 4 Steps Towards Robust Artificial Intelligence. And he really makes a very nice case, kind of a motivation for looking on how to develop hybrid models that connect this symbolic world with the neural one. But actually, in program synthesis, this is something that has already been happening. So I have a few examples here how these hybrids can look. So this one is from the paper Counterexample Guided Neural Synthesis. So what we have here is there's a specification in logical language, and then we use a symbolic solver to generate examples. input-output examples on which a neural network trains and then generates candidate programs. But each of those candidates has to go through the verifier, which is again a solver that checks whether it really is a compliant program, and then this is how we get the result. So this is an example of an interplay between symbolic and neural. And this is another one, learning to infer program sketches. So this one is motivated by patterns that are used by human programmers, who usually kind of, when working, combine patterns that they have learned with explicit reasoning. This paper defines a program sketch. So this is kind of a schematic outline of the full program. So it's not a full program, but has certain pieces missing. And then what happens is that a neural network generates these candidate sketches, and then the sketches are converted to full programs by filling them up using symbolic synthesis. And also the kind of, at least in this paper, it's a nice result that the division of labor between neural and symbolic parts is not fixed, but it's dynamic and is basically determined through learning. So another area of very active research, and I think very promising, is applications of reinforcement learning in program synthesis. So as I've mentioned before, that space of all the potential programs is very large. So methods such as reinforcement learning at least seem to be useful. Here I have an example that I think will be quite influential going forward. So we have a write execute SAS program synthesis with REPL. So basically this is again a paper that takes motivation from how basically people work with code. So people often, when they're programming, they do it in a trial and error way. They have an idea, they write the code, and then they check whether it really is working as they thought. And basically this is how this model operates as well. And also they are inspired by the AlphaGo architecture. So what we have here is that the policy proposes code that should be written, and then value function evaluates the prospect, so the longer term prospect of that code. And in this case, this interpreter that basically is run each time is kind of, it bridges the gap between the syntax and the semantic part of the program here. So this is quite a difference, for example, from that initial neural architecture that I've mentioned, because that one was dependent only on syntax of the language, but now this one here is actually exploring the semantic space of all the programs. And here I have a few more examples of reinforcement learning. So just to go briefly over them, this first one here learns to synthesize assembly code without having needing any human knowledge. So it's similar how AlphaZero learned to play Go. The next one synthesizes a whole library of programs that it needs in order to solve that final problem. Also quite interesting. And the last one has a usage in the testing field of software engineering. So it's about learning an agent that can do fast testing of compilers. So basically an agent that is capable of generating programs in the hope of finding such that they break the compiler, and obviously we can discover a fault. So let me discuss briefly some commercial solutions also. So it's still a bit early for program synthesis in this regard. However, certain big tech companies have offerings that incorporate elements of program synthesis. So, for example, probably the most well-known one is flash fill in Excel by Microsoft, and then Microsoft also has Prose that targets more data wrangling aspects, and IntelliCode is doing a bit of code completion, code suggestion. And Aroma and Code Guru by Facebook and Amazon are similar. I have a question mark here with Google because I know that they're very active in research in this area. So I suspect that at some point they might have also very interesting tools to deploy. And also here are some startups in this area. So the upper four are doing code completion in one way or another. So Synthetic Minds is generating code for smart contracts, Trifecta for data wrangling, DivBlue for testing, and Wizard for user interfaces. And that Micropsy Industries is interesting because they are generating code or programs in a bit different way. They have robots watching people doing tasks and learning from that. Here I have just a brief mention of a very interesting paper by Google. As I've said, they're really strong in researching this area. So they've built a programming by example system that is capable of synthesizing tensor manipulation programs from input-output examples. So I like the quote that they've made in the paper: TF Coder often produces solutions that are simpler and more elegant than those written by TensorFlow experts, including the authors of this paper. So we see kind of a closing of the loop. So we have basically machine learning models influencing software engineering, which is basically about building other machine learning models. However, there is a whole aspect to program synthesis that goes, I would say, quite beyond even software engineering, towards areas related, at least in some way, to more general forms of AI. So here is a nice paper that is about basically synthesizing programs by watching videos. So here I think it's from the Wisdom environment. So an actor moves around in this environment and the model is capable of turning these actions into code. And regarding more general forms of AI, François Chollet published a very interesting paper on the measure of intelligence, where he proposed a new benchmark that would try to measure a bit more general so qualities of intelligence in AI, and program synthesis seems to be quite an important part, at least in his view, in this regard. So definitely it's an area that will have that is very interesting to look at right now and working. However, also one that is associated, I think, with quite a few risks. So some of them are obvious, like to what end will we trust these generated programs? How transparent will they be? However, I think it's very important also to ask ourselves the problems in judging user intent. So at least at current state, all the programs, all the models are focused only on making basically code work according to loose specification. But if at some point we are dealing with very complex programs, maybe even in high stakes situations, we will probably have to have like kind of moral or legal aspects included in some way in these specifications in order to manage risks that will come out from using automatic program generation. So thank you for listening. I hope it was interesting, and enjoy the rest of the event.